Okay, I hope I'm audible to all students who are attending this lecture of Introductory Econometrics. We intend to discuss a few problems from chapter 2 of the book Essentials of Econometrics by Damodar and Gujarati. So in this particular lecture, I will be discussing a few back problems. So worked out problems from the book Essentials of Econometrics by Gujarati and Porter. The edition which I am referring to is the 4th edition of this book. So let's look at a few problems from Essentials of Econometrics by Gujarati and Porter. So I will be not doing all the problems. There are some problems which involve understanding of definitions and all. For that, students can refer to my lecture note. I will be doing more objective problems and numericals from the back problems. Okay. So I intend to look at problem 2.8. Okay. I intend to look at problem 2.8. This is on page number 45. Okay, the problem I am writing it on the screen. State whether. Let me do problem 2.4 first. Let me do problem 2.4. This is on page 44. Okay, so I'm doing problem 2.4 first on page 44. So state whether the following statements. State whether the following statements are true, false, or uncertain. Okay, and give reasons for your answer. So let's look at the question. Let's look at the statements and then let's look at the answer, whether it's true or it's false. Okay, so I'm writing the statements on one side. So statements are as follows. The stochastic error term. The stochastic error term UI and the residual term EI mean the same thing. Okay, and we are going to look at the answers. We are going to write the answers here. Okay, so is this statement true or false? Now all students can recall that UI is the disturbance term you get from the population regression function. EI is the disturbance term or the residual term you get from the sample regression function. Okay, and EI is used to estimate UI. So EI and UI are not exactly the same. So I can write it's a false statement. Because if you look at the population regression function, it is yi equals b1 plus capital B2 xi plus ui, where ui is the population disturbance term. Ui is the population disturbance term. And the sample regression function is yi equals small b1 plus small b2 xi plus ei, where ei is the sample residual term. Ei is the sample residual term, which is used to estimate the population disturbance term ui. So therefore, EI and UI are not the same terms. We can say that EI from the sample is used to estimate UI, which is in the population. Okay, so hoping students have understood this. Let's look at statement B. So statement B is that the population regression function gives the value of the dependent variable. The population regression function gives the value of the dependent variable corresponding to each value of the independent variable. Now let's check whether this statement is true or false. So if you recall the definition of population regression function, which we had done in our lectures on linear regression, we clearly said what? We clearly said that the population regression function is going to give the mean. It is going to give the mean or the expected value of the dependent variable conditional on every value of the dependent variable. So if you carefully look at the statement, it is also false. Since population regression function gives the mean value, it gives the mean value of the dependent variable given each value of the explanatory variable. Okay, so the second statement is also false. Let's look at the third statement. So I erase statement A and I erase the solution also for A, and let's quickly look at statement C. So erasing this part off. So statement C is as follows. A linear regression model means a model linear in variables. You can clearly see this is also a false statement, because again, recall my lectures on linear regression. A linear regression model is a model which is linear in the parameters. It may or may not be linear in variables. It may or may not be linear in the variables. So again, we had done this in our lectures on linear regression. A regression model is said to be linear if it's linear in the parameters. What are the parameters? So for example, I can just write, just for revision, if I talk about this model, it is linear regression. This is a linear regression model since it's linear in the parameters B1 and B2. Since it is linear in the parameters B1 and B2. But if I talk about yi equals B1 plus B2 ka square, xi plus ui, this is not a linear regression model. LRM stands for linear regression model. So guys, this model is a linear regression model because even though it's not linear in xi, it's linear in B1 and B2, which are the parameters. But look at this model, yi equals B1 plus B2 square xi plus ui. Even though it is linear in yi and xi, which are the variables, it's not linear in the parameters. You can see it's not linear in B2, so it's not a linear regression model. So when we talk about a linear regression model, it must be linear in the parameters. We don't care whether it's linear or not linear in the variables. Okay, let's look at statement D. Erasing this part off, let's look at statement D. So statement D is as follows. in the linear regression model, the explanatory variable is the cause. And the dependent variable is the effect. This is also, all students can recall that this is also a false statement. Why is it a false statement? Because clearly we had said in the beginning of the linear regression lectures that the cause and effect relationship between the xi's and the yi's must be justified by the underlying theory. Okay, so in the beginning of our lectures on linear regression only, we had clearly mentioned that when we talk about linear relation, when we talk about a linear regression, it does not show the causal and it does not show the cause and effect relationship. Okay, it just shows the degree of relation between the explanatory variable and the dependent variable. Okay, the cause and effect relationship must be justified from the underlying theory. So when I talk about a linear regression model, we cannot say that the explanatory variable is the cause and the dependent variable is the effect. The only thing we can say is that explanatory variable is related to the dependent variable linearly. Linearly means linear in parameters. That is all what we can say. And we can use explanatory variable to forecast or extrapolate the values of the dependent variable. But we cannot say that explanatory variable is necessarily the cause and dependent variable is necessarily the effect. We can't say that unless and until we justify from the underlying theory. Okay, so statement D is also false. Erasing the initial part, let's quickly look at statement E. So let's see what is statement E given to us. The conditional and the unconditional mean values of a random variable are the same. This is also a false statement. So statement E says that the conditional and the unconditional values of the conditional and the unconditional mean of a random variable are the same thing. You can see that this is also a false statement. Okay, because you can clearly see that expected value of y and expected value of y conditional on x are not the same thing. They are not the same thing unless x and y are independent variables. So only when x and y are independent. So special cases, that only when the variables x and y are independent, I can say that expected value of y is exactly equal to expected value of y conditional on x. But in a normal course, when x and y are not independent, when they are dependent on each other in some or the other way, maybe linear, maybe non-linear, in that particular case, this is the unconditional expected value of y, this is the conditional expected value of y, and they are not the same thing. They are not equal. They will be equal only when x and y are independent. So it's a false statement. Okay, let's look at statement F. Erasing this part off. So statement F. So in the population regression function yi equal to b1 plus b2 xi plus ui, and the sample regression function yi equals small b1 plus small b2 xi plus ei, we are given that capital B's are the random variables and small b's are the parameters. Again, it's a false statement. You can clearly see. The statement is false. Okay, because if you look at the population regression function, B1 and B2 from the population regression function are called the regression parameters, where B1 is the intercept parameter, where B1 is the intercept parameter, and B2 is the slope parameter. And small b1 and small b2 are the random variables which are used to estimate the parameters capital B1 and capital B2. So it's actually the reverse. The question is saying that capital B's are the random variables and small b's are the parameter. It's actually the reverse. Your answer is that capital B1 and capital B2 are the parameters, but small b1 and small b2 are the random variables. They are going to take their small b1 and small b2 are going to have a whole distribution attached to it, and they will be used to estimate capital B1 and capital B2. So small b1 and small b2 are actually the parameters, are actually the variables. Let me correct myself. Small b1 and small b2 are the variables, random variables, which are used to estimate the parameters capital B1 and capital B2. And I have clearly mentioned in my lectures also that the hypothesis testing which we have done in the case of linear regression, we have assumed that B1 and B2, small b1 and small b2 are normally distributed. So you can clearly recall that we had said that B1 follows a normal distribution with mean capital B1 and standard deviation sigma B1 and sigma B1, and B2 also follows a normal distribution with mean capital B2 and standard deviation sigma B2. We had said this, we have done this in our lectures on hypothesis testing and linear regression, which is chapter 3, but I'm using it in this lecture also. You should know that B1 and B2, small b1 and small b2 are the random variables which are used to estimate the parameters capital B1 and capital B2. Okay, let's look at statement G. Erasing this off, let's look at statement G. Okay, so statement G is as follows. In the population regression function, which is yi equals b1 plus b2 xi plus ui, the slope coefficient b2 measures the slope of y per unit change in x. Okay, now you can clearly see that this is also a false statement. Why? Because recall that b1 plus b2 xi is what? Recall that expected value of y given xi is equal to b1 plus b2 xi. Therefore, b2 is what? It is the derivative of expected value of y given xi with respect to xi. So b2 measures what? It measures the slope. It measures the change in the mean value of y. Not only value of y, mean value of y per unit change in x. So this is my correct answer. So the statement G which is given to us is a false statement, because the slope coefficient B2 does not measure the slope of y per unit change in it. It measures the change in the mean value of y. Or I can say it measures the change in the conditional mean value of y per unit change in x. Okay, so this is my correct answer for G. Let's look at option number H. Okay, we're erasing this off. Let us look at option H, which is as follows. In practice, the two variable regression model, in practice, the two variable regression model is useless because the behavior of a dependent variable, the behavior of a dependent variable can never be explained by a single explanatory variable. Okay, so again, if you look at H, now we can't say anything whether it's true or false, because there are some models where the dependent variable might just be explained by one single explanatory variable, and there might be models where one explanatory variable may not be sufficient to explain the behavior of a dependent variable. So I can say that the answer for this is uncertain. Okay, so hoping all students have understood statement H. Okay, basically your answer is just uncertain because you can't say. So I can write there are some models where one explanatory variable may be sufficient in explaining the variations in the dependent variable. Okay, so hoping students have understood this, and then let's look at the last particular statement. So statement I, which is given to us. So statement I is as follows. The sum of the deviation of a random variable from its mean value is always equal to 0. That is, sum of the deviation of a random variable from its mean value is 0. It's a true statement. We have proved it. We have proved this result in our lectures. For just perfection, I can just quickly do the proof. Consider summation xi minus x bar as I goes on from 1 to n. If I have n observations, this I can write summation as I goes on from 1 to n xi minus x bar. If I add n times, I get nx bar, and summation xi is nothing but nx bar, because recall that x bar, which is my mean, is nothing but summation xi by n. So this implies summation xi is nx bar. So summation xi I can write nx bar, and nx bar minus nx bar is. So we have even done this proof in our main lectures, but I've just quickly revised the proof with all students again. The sum of the deviation of a random variable from its mean value will always be equal to 0. So it's a true statement. Okay. So students, this is where I intend to stop in this particular lecture. The objective was to do a practice problem from chapter 2, which is linear regression, the back problems of Gujarati and Porter. We'll do more practice problems in the next lecture of introductory econometrics, practice lecture. Okay. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.